So thanks, Anthony, and thank you very much for the invitation to come to PI. It's great to be here again. Indeed, today I'm going to be talking about fermionic entanglement on the torus. And this is based on some recent work that we did in collaboration with Pascal Fries, who's a graduate student at Würzburg. All right, so just for a very short motivation, we've seen in the last decades a lot of activity right here in the interface between ideas coming from geometry, general relativity, quantum field theory, and information theory. And of course, this is a story that goes way back to the 70s with the discovery of the black hole thermodynamics. Then more recently, a bit more than a decade ago, there was also another boost to this idea via the Ryutaka formula for the entanglement entropy. And more recently, we've also seen many developments on stuff like complexity and black holes and a lot of stuff that actually have been pursued so much here at PI. And there's many other applications. So it's somehow in this context that I want to present this thing today. Okay, so here's the outline of the talk. We're going to start with a brief review for some people that might not be so familiar with the idea of an entanglement or modular Hamiltonian. Then I'm going to present what was the problem, what was the system we were looking at, and what was the question or the puzzle we were trying to answer. So we're going to look at the chiral fermion on the torus. And then I thought about doing the following. Since there's going to be quite a technical calculation here, I'm going to first tell you what the answer is, what the answer to that question was. I'm going to give you the result, and I'm going to explain the properties. Essentially, the new result is an exact formula in a small list for exact known modular Hamiltonians. And after I show you the result, I'm going to explain to you how did we get there. And this is going to be the more technical part. And we're going to see that it was essentially a combination of using the method of the resolvent and complex analysis on the torus. Okay, so let's go to the entanglement, or also called modular Hamiltonian. So when we talk about entanglement, the first thing that probably comes to your mind is the idea of entanglement entropy. That means that we take some density matrix and we choose, this is for the case of bipartite entanglement, so we choose a subset, say a subregion of the system, which for all of this talk I'm going to call the subregion V, and we trace out the Hilbert space of the states that live outside that region. We get a reduced density matrix rho V, and we simply calculate the von Neumann entropy of that. And that's supposed to measure somehow, it's somehow related to the number of Bell pairs that are shared between the two parties, V and its complement. Now, entanglement entropy is just a number, and it's one in a whole family of entanglement measures. So this is only one measure. Another measure is, for example, the Reyes entropies, which are an infinite family of numbers that you get. And if you have all the Reyes entropies, you get the entanglement spectrum, and so on. But what I want to focus on today is not a number, but rather a different approach to entanglement, which is an operator. And this is the so-called entanglement or modular Hamiltonian. The definition is very simple. You take your reduced density matrix and you calculate the log. Now, why would you be interested in this object? Well, you see that written in this way, the density matrix resembles what would be a thermal density matrix, right? For a Gibbs state, you have that the density matrix looks like e to the minus beta h, where h is the Hamiltonian. So that's kind of the inspiration behind, the motivation behind this thing. Now, why is this operator so important? Well, the main reason, I think, is because it appears in the notion of relative entropy. So in information theory, the single most important function of information theory is the Kullback-Leibler divergence, or relative entropy, which is a measure between, it's a measure of the distinguishability of two different probability distributions, or two density matrices. In this case, rho and sigma, and it's defined in this way. And it satisfies a list of very nice properties, like it's positive, and it also only vanishes when rho and sigma are equal, and it has a nice set of properties that make it a nice function to study. And the important thing here is that this function over here can be rewritten as a variation of the expectation value of the modular Hamiltonian on the two different states rho and sigma, and the variation of the entanglement entropy. Moreover, the properties of this function over here imply the so-called first law of entanglement, which means that if you take two states that are very close, so if rho is very close to sigma, and you calculate this trace over here, you will find that the variation, that this vanishes to first order, which means that the variation of the expectation of the modular Hamiltonian is equal to the variation of the entropy for that state. So if you look at this, of course, you see this, this relation tells you that somehow the modular Hamiltonian is to the entanglement entropy what the usual Hamiltonian, the usual energy, is to the thermal entropy. Now, if you're asking, well, where did the temperature go? Because in the first law, we should have a temperature. Well, we're going to get to that in a second. The temperature is essentially inside the definition of K. And this operator has found a lot of applications in recent years in quantum information, many-body physics, due to the entanglement spectrum, and also in ADS-CFT, interestingly, this was one of the main tools and also one of the main obstacles for this program of deriving the bulk geometry from the entanglement structure of the boundary. And it's an obstacle because it's so hard to calculate. Okay, so what's the simplest case in which we know this operator? Well, that is simply Rindler, the Rindler wedge, or the Unruh effect. So that means the following. Suppose you take the vacuum of any quantum field theory you want, living in flat space. And you want to understand, so you take the vacuum omega, and you want to look at the physics of half space. So you want to trace out, in this case, say, all the degrees of freedom that live to the left. So you want to find this density matrix over here. The idea is that you want to find an operator such that this object over here looks like this. Now it turns out that for this particular case, the symmetries of the vacuum are such that since the vacuum is, you can think of it as being prepared by a path integral in which you integrate for a very long time in Euclidean time, you can prove that simply due to essentially boost symmetry, this reduced density matrix takes precisely this form, e to the minus k, where k is given by this expression over here. So this means that the modular Hamiltonian is an integral, a single integral over the entangling region, which in this case is the right half line, of a local expression over here. There's a beta here that depends on x, that's the so-called entanglement temperature, and then there's some operator, which happens to be the energy density. Now the entanglement temperature is given essentially by x, and this is the quantum information version of the well-known Unruh effect, which means that an accelerated observer in the vacuum sees some temperature, which is determined by the value of its acceleration, which in these coordinates is given by the value of x where the orbit intersects this axis, which is precisely x. So for this particular example, the modular Hamiltonian is simply the another charge associated to the boost symmetry. And the thing that I want to emphasize here is that this is what we would call a local Hamiltonian, which means that it can be written as a single integral over the region with only local functions over here. So anything that does not have that form, we say it's not local. Okay, so what other examples are known for this object? Well, there are very few. So as I said, you can start from the vacuum of any quantum field theory in any number of dimensions on flat space. And it turns out that you can map that, in the case of a CFT, of the vacuum of a CFT, you can map this Rindler wedge and get the result for the case when you don't reduce to half space, but rather you reduce to a ball. And that's a well-known result. The other case is in CFT2s, because they are so special, you can go a bit further. So you can calculate, again, the reduced density matrix for a ball, but not on the plane, but rather on the cylinder. And we'll come back to this in a second, but this was a result by Cardi and Tony. And in both these cases, in all of these cases, the Hamiltonian turns out to be a local, which means that it adopts this form where beta is some local function that you have to calculate, which is determined in this case by conformal symmetry. As soon as you take something like a non-trivial arrangement of regions, so for this case, in all these three cases, the region was simply connected. I simply had one interval, right? Maybe in this case it was infinite, but still only one. As soon as you start taking multiple intervals, almost nothing, practically nothing is known. Or if you change the topology of the space where this thing is living, the same thing. There is one neat exception to that, which was worked out in this beautiful paper by Cassini and Huerta, which is the free fermion in 1+1 dimensions. And that's the example that we're going to look at today. So the idea is that if you want to go beyond any of these examples, you're going to end up with something that is generically non-local and non-universal. So you have to just compute it by brute force for a given theory. Okay, so since we have, I told you we're going to work with the free fermion, and I told you that the result for the cylinder was known. So what's the next obvious thing that you would try to calculate? We'll try to do it on the torus, which means now you take the free fermion on the circle at finite temperature. Now I'm going to explain what was the question we were trying to address. So the torus has two cycles, and since the fermion, since you can choose either periodic or anti-periodic boundary conditions, and each cycles, the torus has 4 spin sectors, right? Now, for this talk, I'm going to restrict for the case, so the so-called physical sector, in which on the imaginary time direction, you always take Neves-Schwarz conditions. Okay, so that's going to be fixed, and from now on, I'm just going to refer to either the Ramond or the Neves-Schwarz sector, by which I mean the boundary conditions on the spatial circle. Okay, now the result on the torus was not known, of course, that's the thing we computed, but the puzzle was the following. The torus has 2 obvious regimes, 2 obvious limits. When you take the temperature going to infinity, that is beta going to 0, the torus sort of shrinks in this direction, and what you effectively end up is with the physics of a thermal state on the real line, on the cylinder, right? But that is, as I told you before, that is fixed by conformal symmetry in 1+1 dimensions. So that result was known by Cardi and Tony, and is local and universal. The other obvious limit you can take is when you take the temperature going to 0. So when you take beta to infinity, this donut over here opens up, but you're still left with the circle in space, so you end up with this cylinder over here, where now this is time and this is space. And there was a very interesting observation by Clifferman and Wong in 15, which was that this theory has 2 vacua. It has the Neves-Schwarz and the Ramond vacua. So they pointed out that the result that is universal and given by the Cardi and Tony result is only the one when you take the vacuum in the Neves-Schwarz sector. In that sector, this thing is local and is exactly equal to this one over here. I mean, it's the analytic continuation of that thing. But the interesting observation that they made was that if you look at the Ramond vacuum, that thing is not local, is not universal, and has a very interesting structure. It's actually what we call completely non-local. So what does that mean? Completely non-local refers to something that looks like this, where you have a double integral over the region. So here x and y live in V, and you have 2 operators, one at x and one at y. So you're evaluating a fermion here with a fermion here, and all of them are coupled to all of them because this alpha over here is a smooth function. So this is what we really call continuously non-local. Every point in the modular Hamiltonian is coupled to any other point, every other point within the interval. For this free theory, this is as non-local as you can get. So the question we were trying to understand was, well, how did this happen? how was that you started with a local universal thing at very high temperatures, and then you start lowering the temperature, you have two vacua, and suddenly one of them is local and universal, and the other one is complete, it has a local piece, but the important thing is that it has a completely non-local contribution. And why does this depend on the spin sector? So how was the transition between locality at high temperatures to, say, non-locality in the Raman sector? So to do that, we had to solve the problem exactly on the torus. And so as I said, now I'm going to tell you what the solution is, what the modular Hamiltonian on the torus is. But before that, is there any question on what I just said?
Completely non-local just means like there's no delta functions in it?
Yes, I'm going to get to that right now. Yes. Okay, as Anthony said, there's a delta going to appear here. So the result is a new exact modular Hamiltonian, and the statement is the following. For now on, I'm going to fix the period of the torus of the circle period, the spatial circle to 1, and the torus modulus is essentially given by the temperature. So the statement is that at any finite temperature, the modular Hamiltonian has two contributions, a local and a bilocal piece. This is true for an arbitrary number of intervals, but in particular it's true even for one interval, which is the case I'm going to illustrate in this talk. But essentially, the same formula is true for an arbitrary number of intervals. So the local piece takes the standard sort of Unruh form that we talked about. There's no, this is nice. This is what you would expect, and the entanglement temperature is some complicated elliptic function. Well, it had to be, right? You were working on the torus. What else could it be? The interesting part is the bilocal term. So, and it turns out that it has an infinite but discrete amount of bilocality. So what do we mean by that? So let's focus first only on this term over here, on the integral here. So if I just showed you this part, this is what we would call complete and non-local, right? Because every x is connected to every y if alpha is a smooth function of x and y. This has an extra delta function in there. So what does that do? So this means that this expression is going to be different from 0 only if the argument of the delta function vanishes, right? Now, we're doing a sum here over the integers. So this means that we're only going to get a contribution from x and y such that this function f of x and y is equal to some integer. Now this function depends on the temperature. So here what I'm doing, here I'm plotting the function f beta of x comma y for a fixed temperature beta, for a fixed value of x, and I'm plotting it as a function of y on the x-axis. So if you look at this plot, you'll see the following. So you have to look for the only points, so take an x here. This x is not connected to an arbitrary value of y in the interval. So this over here, sorry, I should have said, this is the interval, and this is inside a unit circle. Okay, the interval goes from here to here. So this means that this point x over here is only connected to those points where the curve of f of beta intersects the integers. So in particular, this solution, and so on. And we're going to get to that in a second. But the only extra thing is that there's a sum over here with an alternating sign of plus minus 1 to the k, the plus corresponding to the Raman sector, the minus corresponding to the Neveu-Schwarz sector. So the kernel is the same, but it comes with a flipping sign for the Neveu-Schwarz sector. Now, what are the properties of this thing? So if you look at the plot, you realize this is a very complicated function, which is a combination of a lot of elliptic functions, but there are two main properties that you can already see from the plot. The first thing is that there's an infinite number of solutions, by that I mean those black dots over here, accumulating at the endpoints. Why is that? The function f of beta happens to diverge at the endpoints, which means that the function intersects an infinite number of integers around there. So there's an infinite number of solutions there. On the other hand, if you plot the coupling alpha, which if you look at the dimensions here, this this looks like some kind of non-local mass, but it has dimensions of energy. And if you plot this thing, you'll realize that this function vanishes at the endpoints of the interval algebraically. And it vanishes in a way that depends on the temperature and on capital L, which is the length of this interval. So that means that the energy of this, the energy scale set by this alpha is sort of redshifted towards the endpoints. And by redshifted, we mean that they are damped, they vanish at the endpoints. And if you think about it, at the endpoint of any entangling region, physics, if you're very close to an endpoint, physics, you don't see the cycles, right? You don't care if this is a torus or the plane or whatever. You just see the vacuum, essentially. And the vacuum is Rindler physics, right? So there's an associated Rindler horizon located always at the endpoints, locally there. So it's kind of like the energy is being redshifted as you get closer and closer to that Rindler horizon. Okay, so that's the exact solution for any value of the temperature. So that explains why I said it has an infinite, because there's infinite solutions, but discrete form of bilocality. That means that it's not, you see this result is not local, it's certainly non-local, but it's not completely non-local, because it's not true that every x is connected to every y. X is connected to some special values of y. That's why we call it bilocal.
You said the redshifting means the bilocal term is dying, is becoming less relevant for higher k.
Yes, exactly. In fact, it decays exponentially with k. Yeah. Okay, so now the question was, well, how does this exact result behave in the two limits that we were talking about? So if you go to the high temperature limit, what happens, this you're not seeing in the formula, I'm just telling you, what happens is that the curve starts adopting this shape. So it gets like flatter and flatter in the interior, but it gets steeper and steeper towards the endpoints. What that means is that the solutions, these black dots, which were the intersections of the curve with the integer, start moving to the endpoints, right? And in the limit, all of them, they all move to the endpoints, but I just told you they vanish at the endpoints. So at very high temperature, what you get is that you completely lose the information about the spin sector, which was exactly what you expected. It doesn't matter if you took Raman or Neves-Schwarz because the temperature is so high that you don't care. And you recover exactly the local result by Cardiantoni, which is fixed by conformal symmetry. So that was nice, but the really cool thing was happening at low temperatures. So what happens at low temperatures is that if you look at the plot here, the curve gets steeper and steeper inside, really in the vicinity of this point over here. What that means is that the black dots, which were the solutions to the intersections, start moving to the interior of the interval. Because say this point over here was associated to this point over here, but now since this curve moved, that point over there, which was the intersection with k equals 1, moved now sort of over here, right? So the points, the solutions, the bilocal couplings start moving towards the interior, but there's an infinite number of them coming from the endpoints, right? Because we said this has an infinite number of solutions. And what eventually happens at very low temperatures is that these solutions condense. By that we mean that in the limit, they reorganize and they form a regular partition of the interval, such that the spacing between the points goes to 0 as the temperature goes to 0. Okay? That's kind of clear from the figure. And so then we have to see what happens to this expression. Well, we said that for each one of these black dots, there's a contribution coming from the delta. There's a peak there, right? There's one contribution, there's like a peak there's like a delta at each value of these black dots. So then if you think about what's the effect of having a series of peaks that are, whose distance is shrinking to 0, it means that you're having something in which you grab the value of the function at each point on the interval. Right? You get one contribution of the function per point. So, and if you do the math carefully, you realize that actually this expression over here reproduces exactly the definition of the Riemann integral. Because that's what we mean when by a Riemann integral. You integrate the value of a function at a given point, and you multiply it by a small delta that is going to 0, and you do that sum. Well, that sum is exactly what you get from this sum over here. It's not obvious to see, but I'm just telling you. And it turns out, and that was the nice spin to the story, is that still there was a plus and minus 1 here. So that means that in the Ramond sector, you get contributions all with the same sign, which reproduces the Riemann integral. Whereas in the Neves-Schwarz sector, you get a function that is wildly oscillating for different values of k. And since you have to think always that this is a kernel, that you have to think of this as a kernel acting on smooth functions, when you integrate something that is oscillating like crazy against any smooth function, this is exactly 0. So in one case, in the Ramond sector, for the plus, we get the Riemann integral, which reproduces exactly the non-local term, the two integrals we talked about before. Whereas in the Neves-Schwarz sector, the oscillation of this thing cancels exactly this operator here. And that explains why in the Ramond sector you had a completely non-local term, which had two integrals, whereas in the Neves-Schwarz sector you had 0 for this term over here. This disappears for the antiperiodic sector. Okay, so that's the story of the result. So before passing to the more technical side of the story, any questions about this?
Can you maybe say a few words about what the interpretation of this result is? I mean, before you do technicalities, what's the physics of this state?
I think that it's telling you something like, yeah, that depending on, so when you do, here essentially there's a scale, well, I didn't plot it here, but the physical scale here is given by the temperature, right? So I think you could put it like this. Suppose you're at low temperatures, not exactly 0 temperature, but at low temperatures. The exact result is an infinite number of bilocal stuff. But depending on the scale with which you're probing this system, you might either see something that looks completely non-local, or you might be able to resolve the bilocalities.
We can postpone the discussion till later, but I'm just wondering what it has to tell me about entanglement. What's entangled with what? Fine.
Oh, well, maybe we can postpone that. Yeah, no, but it's a good point, yeah. Okay, so now let's step into the more technical side of how did we find this result. And this is going to be a combination of something called the resolving method and doing complex analysis on the torus. Okay, so for free fermions, there's two things we have to, there's two important aspects for us. The first one is the fact that if you're on the torus, the propagator is completely fixed by the periodicities that you choose. So give me a sector. In this case, as I said before, we're going to only restrict to the Ramond Neves-Schwarz and Neves-Schwarz, Neves-Schwarz, where this I mean space and time. Once you fix the periods, the boundary conditions, and the requirement that you have a simple pole, because the propagator has to diverge when x goes to y, those two requirements completely fix the propagator. And it's giving in terms of some elliptic theta functions. On the other hand, when you study the reduced density matrix of the free fermion, in principle, the reduced density matrix should be something that reproduces the expectation values of all local operators in the region. But it turns out that for the fermion, it is enough to find an operator rho v that reproduces the two-point function on that interval. Okay, so this is something very special to the fermion, which is telling you essentially that rho v is completely determined, uniquely determined by the two-point function. Now, moreover, the modular Hamiltonian, which is the log of this density matrix over here, turns out to be a quadratic operator in the fermions, which means it has to take this form. I haven't told you, so this is like the operator k, that's like mathcal k, and by capital K I mean the kernel, seen as an operator acting on functions, and this thing has to be quadratic. Now, if we don't say what k is, we can't yet say whether this is local or non-local, right? Because it depends on this kernel. And moreover, this kernel over here, and this was shown by Peschel, takes this form. It's essentially the log of the inverse of the propagator, of the inverse of the propagator, seen as, usually we think of the propagator as simply a function, a number, but here we're thinking about the propagator as an operator acting on functions. So as an operator, you try to take the log, and that's going to give you k. So for us, of course, there were two questions. Well, how do you compute this log? And moreover, how do you do that on the torus? Okay, so to answer the second question, we use the resolvent method, and for the case of the fermions, this was really put forward by Cassini and Huerta. So you have to ask the question of, well, how do you take the function of an operator in general? And one way to do that is via the resolvent method. So this is a super nice technique that people use. Given a holomorphic function, f, well, here I'm just taking the log of the, say this function over here. If you have a holomorphic function that is holomorphic in a certain set of the complex plane, and you have an operator, you want to define what do you mean by the function of the operator. And how do you do that? Well, you just use Cauchy's integral formula. So for a second, suppose that G was a number. Let's suppose it was one of the eigenvalues of the operator G. So then this equation is obviously true. So what do we have here? So this is simply Cauchy's integral formula, where the function that I had here, I simply put it here. So psi is the dummy variable. And R here is what we call the resolvent, but for now, suppose it's just the inverse. It's 1 over psi minus g. If you take this expression, you plug it back here, you do the contour integral, you trivially get the left-hand side, right? Because you have a simple pole like psi equals g. So the idea is that you generalize this formula for the case of an operator, when g is not a complex number, but rather an operator. So that means that this is a complex function. This is the operator content is really in the resolvent, in finding the inverse of essentially g minus the identity multiplied by some number, psi. So in the case when you have an operator here, what you have to do is that, well, you solve the problem of the eigenvalues of that operator. G is going to have some eigenvalues in the complex plane somewhere, and if these eigenvalues lie within a compact subset, like this that I drew here, then for this formula to work, the contour gamma has to be any contour that wraps around the entire spectrum. It has to catch like really all of the eigenvalues of the operator. Okay. So we're going to use this formula. And now we have to say, okay, so we changed the problem. I told you I wanted to calculate the modular Hamiltonian. That's given in terms of a log of some function of the propagator. And I changed you that problem to the problem finding the resolvent of this guy. If I can find this operator here, I simply plug it in here, I do whatever contour integral I have to do, and I find the result. Now, so now what does this thing mean explicitly? So since R and G are operators, and here we're thinking again of them as distributions, as things that you integrate against regular functions, the meaning of this equality here is this thing over here. So what does it mean to find the inverse? It means that you find an operator R such that if you took psi minus G and you multiply it with R, it gives you the identity. But here, of course, we're dealing with kernels, so multiplication has to be understood in the sense of multiplying functions and integrating them. So the meaning of this equation is what is written here, where you see that there's two sort of external points, which are x and y, and there's one dummy variable, which is z, which is being integrated over, and there's one parameter, which is chi. So this psi, we're gonna leave it there for now. Eventually we have to plug it back into this integral, but for now we're gonna forget about it. So you see, this means that R multiplied by psi minus G, where I have to put an identity here, and identity in terms of functions means the delta, has to be equal to 1, again the delta. So in principle, finding the resolvent means we'll find any function of x and z that satisfies this equation. And that's a hard problem. That's a really hard problem in general. But if we were able to do that, if we would find the resolvent, then the modular Hamiltonian, the entropies, etc., easily follow from contour integrals. So that we know how to do very easily. Now this problem was solved, as I said before, on the plane by Cassini and Huerta, and on the cylinder by Clifford and Wong. And we were trying to solve this thing on the torus. So here comes the interesting stuff. So I told you before, I gave you an equation in terms of R, and by doing a simple change of variables, so I just insert a delta here, forget it, this is a very simple, I'm just going to redefine what I mean by the resolvent by isolating a delta, a Dirac delta. Okay? So this x and z generically has a piece has a contribution that goes like the delta of x minus z. So I factor that thing out, the rest I call f, and I rewrite the previous equation in terms of f instead of r. What you get is this equation over here. So I'll just go back for 1 second. So this equation, which had r and g, now becomes an equation that has f and g, because I changed r for f. Now, what's the value in doing that change of variables? Is that now we're supposed to solve this equation. This might look even harder because this is technically a singular integral equation. It's obviously an integral equation, but it's singular in the sense that the propagator has a pole, right, when x goes to z at coincident points. So when you're doing this integral, you're going to encounter some singularity there, which you have to regulate. So in principle, okay, we have to find f that solves this equation. And this would be very hard, but, and here comes the key observation that led to everything else and the solution possible, is that after you look at this equation for a while, you eventually realize that this actually looks like something that came from a contour integral that had 0 residue. And this was really the key observation of the paper. What do I mean by that? Suppose you were doing a contour integral of this form. Suppose you were integrating the product of g times f. Remember now that there's two external points, which are x and y, which were not, these are spectators in the entire calculation. And there's one integration variable, which is z. So suppose you were doing an integral like this, along a gamma that wraps around the entangling region V, right? Now suppose, moreover, that this function, the combination of these two things, gf, so that's going to be really the important thing, gf, this combination, seen as a function of z for a fixed x and y, suppose it had some pole somewhere. Well, if you were doing this integral over here, where now I'm moving x and y outside V, because as I told you, you have to regularize this thing, but you put some epsilons and eventually you take them to 0. So suppose, for example, G had a pole somewhere, and indeed G has one, because G is the propagator. It has a pole precisely when Z goes to X, right? So if you were plotting this function, and so G is going to have a pole, let's suppose it's here, when Z goes to X. So this integral over here, this would be a simple pole, which would give you, when you did this integral, you would get the residue, you would get an f evaluated at x, y, which would give you this term over here. If, moreover, the same thing was happening with f, so if f had a pole when z goes to y, which I'm drawing here as this point over here, if f had a simple pole there, again, the same thing, you would get 1 over, say, z minus y here. You would calculate that residue, and the contribution would be precisely g evaluated at x, y, which was the location of the other pole, which would be this point, this term. So that would explain these two contributions over here. Now, how are you going to get this? Well, you need a branch cut. Because you see, when you were doing the contour integration here, you would get a contribution from this pole, which would be this term. Contribution from there would give this. And moreover, you needed to have a branch cut such that you integrate very close to V, and that term gives you this thing over here. So the point was that this complicated singular integral equation would be a trivial application of a contour integral if you're able to find a function f such that gf looks like this. Right? So now the task was, well, how do you find that thing? So the task was to now find a function f such that we get the correct poles and the correct cut. And if we're able to do that, we solve the problem. Okay, so how do we find f on the torus? So this was really the interesting stuff. So as I said before, what are we looking for? We're looking for a function. X and y are fixed. We're looking for a function of z that has 0 residue on the torus. What's the obvious candidate for a function that has 0 residue on the torus? An elliptic function, right? So, because it's a theorem, but it's very easy to show, that an elliptic function has 0 residues in any fundamental domain. The reason is very simple. I mean, an elliptic function simply means that, well, can you see this? With the, oh, maybe not. Yeah, I guess or maybe, no, I'll just draw it here. You can see here. So the point is that elliptic functions means that they're doubly periodic, but they're also meromorphic. So they're holomorphic on the torus, but accepts possibly some, some isolated points. Which means, like, if you draw them in the complex, if you think about the torus as the complex plane quotiented, right? So the reason why they if you look at an elliptic function on the torus, the idea is that these things are going to have some set of poles, but the theorem says that if you do a contour integral within one fundamental region, they have to have 0 residue. And the reason is very simple. It's because on the one hand side, think now that you were doing an integral like this, with a bigger and bigger square. On the one hand side, since you would be integrating something like this, right? Where f is elliptic. On the one hand side, if f is elliptic, it has to be doubly periodic, which means that the contribution, say, from this side has to be the same from this side and the same from this side, because we're on the torus, right? And the same in the other direction, which means that this thing would have to grow as the perimeter of the square, right? Because we're doing a line integral, and these things are simply repeating themselves. So on the one hand side, that has to go as the perimeter, but on the other hand, you say, oh, but if this had some residue, I can just evaluate this by residues. So I calculate the residue here, I calculate it here, here, they're all the same. And how many do you get? Well, that grows with the area of the square, right? So, oops, it's the fact that, of course, no function except a constant can satisfy this thing, right? So the point was that we were looking for a function that had zero residue in the fundamental region, and there's an obvious candidate. It has to be an elliptic function. And the issue is that there's very few elliptic functions. Okay, so then the question is, what are the exact requirements such that the thing that we postulate becomes equal to the actual equation we wanted to solve? What's the recipe to find that function? Okay, so there's three essential things. So we're trying to look for f, right? The first requirement is that we want the combination of g times f to be exactly doubly periodic. It has to be elliptic, that's what we said. But now the propagator on the torus, depending on the spin sector that you chose, might flip signs, right, in the different cycles. And obviously something that is flipping sign is not doubly periodic, right? Its periods are larger, but you want something that is doubly periodic in the fundamental region. That simply means that you have to find a function that has the same periodicities as g, such that it cancels the possible minus signs that appear in the propagator, such that the combination g times f is doubly periodic. So we know what the periods of f have to be. They have to be exactly the same as those of g for a given sector, for each sector. Second, as I said before, f has to have a pole, because I told you the propagator already has a pole, that's taken into account. We need to find an f that has the correct pole, as I said before, at y. Okay, so it has to have a singularity, and it also has to have a branch cut. And the last requirement is what is the nature of that branch cut, in order for this contour integral to become this regular integral over the region V. So the last requirement is that you see, if you're doing the contour integral over here, this is in general not going to give you the usual integral over the region, unless something very special happens. Suppose the value of the function here, f, is essentially equal to the value of the function on the other side. By that I mean, if the ratio of the value of f just below and above the cut is a constant, that's going to imply that when you come integrating in this direction, you're going to get something that you're going to call integral of g times f along v. And when you turn around and integrate in this direction, you're going to get essentially the same thing, up to a factor. Right? If these two functions, if f did not have this property to essentially be the same up to a constant above and below, then this trick would never work, because you would never get the usual integral over the interval. The last thing that we want is that there's no extra contributions in this formula, which means that we want the function to be smooth around here. Of course, it's going to have a cut at the endpoints of the interval, but we want it to have no singularity, because we don't want to have any extra term over here. So this is the recipe. These are 3 or 4 conditions, and it turns out that the solution is unique. There is a single function that satisfies all these properties, and I'm going to flash the formula just to convince you that there's an actual equation behind these things. Of course, it involves a complicated combination of elliptic theta functions, but that's fine. That's exactly what you would expect. So instead of analyzing this thing over here, I decided to simply plot the function to try to convince you that we actually found it. So what I'm going to plot here is the result of g times f, for a fixed value of x and a fixed value of y as a function of z. And since this thing is a complex function, I decided to use the standard way of depicting complex functions. But now I have to explain to you the notation. Okay, so the two axes, this is essentially the complex plane of Z. The two axes physically mean the spatial circle and the imaginary time circle. I'm fixing beta to 1. So this is supposed to represent one fundamental domain of the torus. Right? You have to identify this line with this line and this one with this one over here. Now, what does the plot mean? So at each value here, at each point Z, the combination GF is simply a number. It's a complex number, okay? And write it in polar decomposition. So the color here is labeling the value of the phase of e to the I theta. So red corresponds to theta equals 0, and I don't know, well, you see that it varies smoothly. Okay, so the color is representing the value of the phase of G times F. And then for a fixed color, the brightness of the plot is indicating the absolute value, the R. So black means that, or very dark, means that you're close to R equals 0, which means that the value of the number is close to 0. And very, very light or white means that the function is very large. So now let's look at the plot. First thing is that I hope you're able to see that this thing is actually periodic. Doubly periodic, I mean. So suppose you are looking here. So you see you have like these two purple corners which appear again on this side. And then this bluish part which appears again here. If you look at the other sides, well, you see this kind of red thing coming out here, coming in here, the yellow, the same thing. So if you look at it for a while, you convince yourself this thing is doubly periodic. That was the first requirement, so at least we have the periods correct. The second thing is that it has a branch cut. Well, it's clearly there, so this is just what I chose in this plot for the entangling region. So the branch cut is lying exactly at the entangling region. What else do you see? Well, you see there's two zeros, which are irrelevant for our calculation, but I'm just telling you, there's two like black spots over there, right? But more importantly, there's two poles, which one is over here and the other one over here, which are precisely the two poles that I was talking about before. Now, how do you see it's a pole? It's not so obvious, but if you look at the color close to here, it looks very bright, almost like a white spot over there. So this is indicating the two simple poles of this function that we needed. Another requirement was that nothing bad was happening at the endpoints, which was that we didn't want to have singularities at the endpoints of the cut. And that's precisely the case. So of course, there's a branch cut here. That's obvious, you can see it there. But there's no singularity happening there, which was one of the other requirements. It's just a fixed color over there. And the last property, which is unfortunately not obvious in this way of plotting, but just you have to believe me, if you take any point just above the cut and the same point just below the cut, the ratio of the functions is a constant all over the cut.
Is it a real constant or it's just something?
It's actually real. Yeah.
It's real. There.
Actually, yeah, you can see that it's real, right? Yeah. Yeah, the colors match. Okay.
Sorry, the other two are the zeros, these 2 points on the left.
Yeah, the zeros are this one and this one.
The other, you have
Sorry, the poles are this one, the zeros are here, but the zeros play no role in the analysis.
they were not part of your requirements.
No.
They just,
No.
are they important to get this ratio?
No. It's just... Okay, I don't want to say something wrong, but I think that it's related to the fact that if you have an elliptic function, you have to have some zeros over there. There's going to be some poles, there's going to be some zeros. So I think you could not make this plot without getting two zeros over there. Okay, so well, I hope that I just convinced you that we found the function. And once you have the elliptic function, it's an exercise. You just have to put everything together and go back. We said at the beginning, the modular Hamiltonian is given by the log of a certain function of the propagator as an operator. We found R, that's the plot I just showed you, and then it's a simpler exercise to plug it back into this contour integral, do the integral, and once all the dust settles, what you find is the thing I showed you in the beginning.
Sorry, can I ask a question? How do you know that solution is unique? So you found the solution.
Yeah. That's something. Okay, I'm sure there's a better answer, but I think it's similar to what happens when you take the propagator. Like, if you ask for what are the elliptic functions that have poles in specific places, these things are unique and given by the Jacobi elliptic functions.
I mean, I can ask, maybe there is a meromorphic function on the torus, right? That doesn't have branch color. Well, I mean, just a meromorphic function.
I don't know, of course, but that would not solve the problem we were asking for, right?
Why not? Why can't I have a meromorphic function exactly at the same, at the same point?
Yeah, but we wanted it to have the cut, right? We needed to have the branch cut.
So I'm saying whatever you have plus.
No, because that would have some other poles.
But I can adjust the meromorphic function in such a way that we have poles at the same location. And I can readjust the strengths of the residues and so on.
Yes, but, okay, very good. But then you would have to be very careful. I mean,
well, so you either have a proof that it's unique or you don't.
Right, no, explicitly no. No, but I think it's easy to see that it's unique. But, right, no, we didn't specify this in the paper, no. But if you were to put a meromorphic function on top of this, you would have additional poles. And you would get extra contributions to this equation. That's my take on this. Yeah. Okay. I'm just going to flash out. We're getting to the end. Once you have the resolvent, you can calculate a bunch of other stuff, and in particular, you can get for example, the entanglement entropies, which were not known. And they happen to have this nice property that, so you calculate the entanglement entropy, you get a universal term, a spin-independent term plus a spin-dependent term, and the spin-dependent contribution to the entropy, interestingly, depends only on the length of the entangling region and not how you chose to, what is the configuration of the intervals. In particular, like, these two entropies would be the same provided that the total length of these two things is the same. You can also calculate exactly relative entropies, which is nice because they're one of the few quantities that are well defining in a QFT. So there's a bunch of other calculations that we did, and they work out nicely. So, okay, to wrap up, what we did was to study the entanglement of the fermion on the torus via the resolvent. The results, so we compared with the results that were known for the modular Hamiltonian and the entropies on the cylinder. The result was a new entanglement Hamiltonian, at least a new exact solution. We saw that it involves an infinite set of bilocal couplings, and that it shows you how the modular flow transitions from locality at high temperature to non-locality at low temperature. And we solved that problem via complex analysis on the torus. So I had some slide of an outlook, but I think I'll leave it at that. Thank you very much.
All right, any questions?
You say that you've computed something for disjoint intervals.
Yeah.
Don't Shouldn't you have a different function for these young intervals? Because I thought that you needed a cut for each interval.
Sorry.
Well, from what I understood is that your function had a cut.
Yes.
Entanglement.
No, sorry. I meant that the end. Yeah, sorry. So here, is this what you mean? Yeah, I meant that when you calculate the entanglement entropy, not the modular Hamiltonian. That's another story. That's very different here and here. Here it's universal. Here it's what we found. Okay. What I meant is that if you calculate the entanglement entropy of this system, you get two contributions. One of them does not depend on the spin sector and does depend on the configuration of the intervals. It's very different here than here for the same total length, I mean. There's an extra contribution which was in fact the function that was not known. And that was the really new thing that we found in this paper, which is the part that depends on the boundary conditions. And that entropy is equal for these two configurations.
Were you able to check that? Or you're saying I computed the left-hand side, then I have a prediction for the right-hand side? How should I understand this?
No, it's because you do this calculation, and the formula explicitly only depends on the sum of the lengths, and not on their configuration or their spacing or something like that.
I just thought that if you had these joint intervals, you may have to have a function f that needs to have various cuts, where each cut goes.
No. Indeed. The function f that solves this is very different from the function f that solves this. But once you take that thing, put it in the resolvent, put it in the contour interval, and do all that calculation, this contribution ends up being independent of that. And I don't have a good answer why. Yeah.
Still need to consider, does it have a gravitational anomaly or not?
Sorry?
Does it have a gravitational anomaly? Or C left and C right are the same? Or?
Yeah, no, we're in flat space. We were actually only considering one chirality here.
Yeah, so C left and C right are not the same.
Well, yeah, I guess.
It's like a chiral Fermion, really.
Yeah. I guess you could also think about that, yeah.
I had heard some claim that there is some problem in defining entanglement entropy for these systems. I mean,
Okay.
in calculation, I don't see any of that.
No.
Well, okay, related to that, that usually is a problem with the divergent terms. So, where do those show up in your modular Hamiltonian? Like, where are the divergences in your modular Hamiltonian?
So,
is it only in the local term?
no. It's universally gonna have a divergent. The operator itself doesn't look so divergent, but as soon as you calculate the expectation value of k, this is divergent.
Does it only come from the local piece, or it's like the non-local part divergent?
Good question. I think it comes from a local piece. I think so, but I don't quite remember. I would expect it to come from the local just because you're evaluating the thing at the same point. Yeah, but I'm not sure. I would need to check the, yeah.
Okay, any other questions? Now let's thank the speaker again.
Thank you.